So now we'll look at explosions under the scrutiny of individual concepts that are related to momentum, which are the change in momentum, the impulses, and the rates of change in momentum. So for the changes in momentum, we know that change in momentum is P minus P0. And if the initial momentum was 0 in the case of those explosions, then the change in momentum is the momentum. And what we said about the momenta is that they are equal and opposite to each other. Therefore, the changes in momentum are equal and opposite to each other. So that's what we would say about the changes in momentum. Now let's take a look at the impulses. Impulses are defined as the amount of momentum imparted to a body. So in the case where we had our two particles, well, let's see, the amount of momentum that was imparted to number 2, the momentum that was imparted to number 1, well, they both change by the same amount, and so those impulses are equal and opposite to each other. So the impulses are equal and opposite to each other as well. Now that is true of the impulses imparted. So we have 2 imparting an impulse to 1 and 1 imparting a pulse to 2. So those imparted impulses are equal and opposite to each other. Those received. So number 1 received an impulse. Number 2 received an impulse. So the received are also equal and opposite. So the impulses are equal and opposite, both those imparted and those received. Now lastly, we have our rates of change in momentum. So let's look at particle 1 and particle 2. The rates of change in momentum are delta P1 over delta T1. And for the second one, we have delta P2 over delta T2. Now when we are looking at this interaction between the two particles as they are exploding, so this 2 is exerting a force on 1 that causes it to move to the left, and number 1 exerts a force on it as it moved to the right. So what about the time involved? The time that particle 1 is imparting a force onto 2 and 2 onto 1 are the same. The times are equal. Just as you might imagine two people are shaking hands. The amount of time that person A is shaking B's hand and B's shaking A's hand are equal to each other, because the moment that one of them stops, the handshake ends. Even if the second person didn't try to stop it, it ends. So those delta T's are equal to each other. Well, and we just said again above in the beginning that the delta P's are equal and opposite to each other. So the rates of change in momentum, if we rewrite those, we have delta P1 over delta T and delta P2 over delta T, because the delta T's are equal. And we said the delta P2s are equal and opposite to each other. And you may recall that quite some time ago we defined force as the rate of change in momentum. The net force is the definition, the rate of change in momentum is the definition of the net force. So therefore, we have F1 is equal and opposite to F2. So whenever there's an explosion in this case, we might say for every force, there is an equal and opposite force. That is more famously known as for every action, there is an equal and opposite reaction. And this whole observation that we came to in the end is known as Newton's third law. For every action, there's an equal and opposite reaction. For every force, there's an equal and opposite force. And so again, we see another of Newton's laws that comes as a consequence of momentum. And so we notice that in every case of interactions of particles, there are action-reaction pairs. Action-reaction pairs exist whenever there is a change in motion. And so that completes our examination of explosions. So we saw in the beginning that the momentum of the particles are equal and opposite. The changes in momentum are equal and opposite. The impulses are equal and opposite, and the forces are equal and opposite whenever we have an explosion. In our next installment, we will look more closely at interactions of particles where we have a bouncy collision.